Hey guys, welcome back to my channel Euclid Mathematics. In my today's video, we are going to learn how to find cyclic subgroups of a different group, like a dihedral group, group of integer, group of Q4 means quaternion group of permutation group, and so on. Okay, but in my today's video, I will explain how to find out cyclic subgroup of a quaternion group, which is having order 8. Okay, so it contains 8 elements, Q4, or generally we call it as the Q8. Now let's go to our example. We see how we can find cyclic subgroup. Okay, so here we have the group Q4, which is the quaternion group of order 4. Okay, so it contains total 8 elements. It is a plus minus 1, plus minus I, plus minus j, plus minus k. That means order of Q4, if we count here, we get the total 8. Okay, so here plus minus 1 means 2 elements here. So total number of 8 elements in our group of order 8. Okay, so order of Q4 is a 8. So we want the cyclic subgroup of quaternion group. That means cyclic subgroup we use to find that cyclic subgroup by using Lagrange's theorem. Okay, and Lagrange's theorem, it says that order of group divided by order of H. Okay, that means the element which present in that group. Okay, so Q4 it is here as a group and it is order 8 here. Okay, and H is the subgroup of Q4. Okay, that means we want here cyclic subgroup. Okay, so H is the subgroup, and by Lagrange's theorem it says that order of G divided by order of H. H is here the element of the order which present in our group. Okay, so what is the possible order for all elements in our group? We know that a raised to n, which is identity. When it comes identity, we have to check their powers, and these powers are actually the order of our group. Okay, so order of that certain element. Okay, so here identity element in a Q4, which is a 1. Okay, so 1 is the identity element in a Q4 because it is a multiplicative group. So 1 is the element whose order is 1. Okay, 1 is the element whose order is 1. Minus 1 is the element whose order is 2 because minus 1 square it is a 1. Okay, and 1 is the identity element. Okay, so a to the power n identity means the group element which gives a to the power n identity, which is the order of that element. Okay, so a to the power n, that means minus 1 to the power 2, which is identity. Again, I square, we know that the I square is minus 1, then I raised to 4, it comes 1. Okay, that means plus minus I, plus minus j, and plus minus k. Okay, these 3 elements whose order, that means total 6 elements. Okay, whose order is a 4. Okay, we have to take their 4th order, then only we get the 1. Okay, so these are the possible order for our element of our quaternion groups. Okay, but by Lagrange's theorem we can find it easily. We have to just find out the divisor of 8. Okay, so divisor of 8, which is a 1, 2, 4, 8. Okay, and in our quaternion group we have the divisor which is a 1, 2, and order which is a 1, 2, and 4, but 8 it is not possible. Because of that group of order it is 8 here, but there does not exist any element whose order is 8. Okay, so by using Lagrange's theorem we can say that 1, 2, 4, which is the possible order of elements. Okay, now let's find out the order of each and every element separately. Okay, so here Q4, we have one note here. Q4 is the element of order 1, 2, and 4. Then Q4 has a cyclic subgroup of order 1 to 4. That means if we have the element whose order 1 to 4, which is present in our group, then and only then it is possible it has a cyclic subgroup of order 1 to 4. Okay, if the element of order it is not present in our group, that means we cannot say that the order of these elements are present in our group. Okay, that means we have the element of order 1 to 4, that means it is possible only when we have it is the subgroup of order 1 to 4. Okay, so when subgroup order 1 to 4 is possible only when the element are present there. Okay, now subgroup of order, let's find out the subgroup of each and every order. Okay, so we have to work for 1, 2, and 4. So we know that identity and group G always are subgroup of a group G. Okay, so it is easier, we know that it is a standard result, but we have to go through the process. So here subgroup of order 2 in Q4. Okay, so we have to find out the subgroup of order 1, subgroup of order 2, and subgroup of order 4. Okay, so let's go for the subgroup of order 2 in Q4. Okay, so we have to use the result from group theory which we use to find out the cyclic subgroup or subgroup of order for some certain element. So that result is here. So you can see here the result, cyclic subgroup of order D in Zm cross Zn, which is equal to Zm cross Zn. That means you can take any group here. I took it here integer group. Okay, so we can take it any of the group, like a dihedral group, like a quaternion group. Okay, so here cyclic subgroup of order D in the given group, which is a number of element of order D in G divided by phi of D. Okay, So we want the number of element of order d in G, and we have to take that phi of d is here. So what is mean by phi of d is here? It is Euler phi function. So Euler phi function, I will explain how we can find that Euler phi function here also. So let's go for the solution. So here we want the subgroup of order 2 in Q4, okay? That means number of element of order 2 in Q4 divided by phi of 2 as our previous result, okay? So number of element of order 2 in Q4 is only one element is there, whose order is 2, minus 1 is the only element whose order is 2, okay? And of phi of 2 which always remain 1, okay? So I will explain how to find that Euler phi function, okay? So here phi of 2 is 1, which is equal to 1 divided by 1 is 1, okay? So we got the only element in our group of order 2 which is a minus 1, okay? So H2 is a minus 2 minus 1, okay, whose order is 2, okay? Ideal generated by minus 1, and we know that ideal generated by minus 1 is a minus 1 raised to 2 is a minus 1, minus 1 raised to 2 is a 1, and minus 1 raised to 1 is 1, minus 1, okay? So I got the first element, first subgroup here, H2, which is ideal generated by minus 1. Now next possibility is here 4, okay? So we have the element of order 4, okay? It is not possible because there does not exist any element whose order 8, okay? So it does not possible. So now only here for 4, so subgroup of order 4 in Q4, okay? So we can go through this way also, number of element of order 4 divided by phi of 4, but the more easier way for finding the subgroup of order 4 in Q4, that means H is a subgroup of order 4, then we know that if group is having order 4, if group is having order 4 which is isomorphic to either Z4 which is a cyclic group, or which is isomorphic to Z2 cross Z2 which is a non-cyclic group, okay? So these are the two possibility for our group where which can isomorphic, okay? Now let's check if our subgroup is isomorphic to Z4, then what happen, and our subgroup is isomorphic to Z2 cross Z2, then what happen, okay? Now let's go for the next part. Now here, cyclic subgroup of order 4, okay? Cyclic subgroup of order 4 means it is a Z4, okay? So for finding cyclic subgroup of order 4 in a Z4, we know that the number of element of order 4, okay? How many element of order 4 are there? So you can take the Z4 group or you can take the Quaternion group, okay? So we can get that answer here, plus minus 1 raised to 4 plus minus j raised to 4 plus minus k raised to 4, okay? That means all element is having order 4, okay? Because their fourth power gives identity. So here 2 element, 2 and 2, total number of 6 elements are there whose order is 4, okay? So number of element of order 4, it is here 6, okay? And divided by phi of 4, okay? Now I will explain how to find phi of 4 here. So for finding phi of 4 by using Euler function, okay? So phi of 4 can written as, so we have to write the by division method. So 4 it is here, divide 4 by possible number, smaller number. So I found it here 2. So 2 2s are 4. Again possible number which divides 2, which is a 2 also, okay? So 2 1s are 2, 2 2s are 4, okay? So I got the total division here till 1, okay? So for Euler phi function for phi of 4, we want phi of 4. That means we got the P1 which is a 2, okay? So here P1 2. That means which number, different number are appear here, we have to take it as the P1, P2, P3, okay? And n it is always here 4. Phi of n is equal to, so n it is there. Phi of n is equal to n into 1 minus 1 upon P1, 1 minus 1 upon P2, and so on. This is the Euler phi function. So I took it here. So we have here P1 is a 2, okay? And n is equal to 4. Substitute these values here. Here P1 is 2, okay? So P is 2 here and n is 4, okay? So n is 4 and 1 minus 1 upon P1, okay? P it is here 2, okay? And remaining P2, P3 are not there. So all are 0. So we do not have to worry about this one. So, okay, this is not the part after of that. So here n is 4, 1 minus 1 by 2. 1 minus 1 by 2, it remain 1 by 2 multiplied by 4. So 4 by 2 is a 2, okay? So that means phi of 4 is a 2 by using Euler phi function, okay? Now let's go for our example. So in our example, 6 divided by phi of 4, which is a 2, okay? 6 by 2, which is a 3, okay? So we have the cyclic subgroup of order 4, which is total 3, total number of 3, okay? And which is from there plus minus I, plus minus j, and plus minus k, okay? These are the cyclic subgroup, okay? Now let's find out which are the cyclic subgroups are there. Okay, first it is ideal generated by I from here, plus second is j, and third is a k, okay? So the element which can be generated by I, okay? Ideal generated by I. Ideal generated by I, we know that I raised to 1 remain I square, it is minus 1, I cube, which is equal to minus I, and I raised to 4, which is a 1, okay? So these are the element which generated by I, okay? Similarly here, it is the second subgroup, okay? So which ideal generated by I. And now next subgroup, ideal generated by j. Similarly, like we have to run the power of j. So which gives 1 minus 1 minus j, okay? And similarly for H5, ideal generated by K, okay? Which is a minus 1, 1, minus K and K, okay? So I got the 3 cyclic subgroup whose order is 4, okay? 3 cyclic subgroup whose order is 4. You can check it here. The number of element which present here, total number 4. Number of element is 4. So our cyclic subgroup is having order 4, okay? So 3 elements are there. Now it's now left over part is here the non-cyclic subgroup of order 4, okay? Because our group is isomorphic to 2 different groups. Order of H is a 4. That means H is isomorphic to 2 different groups. One is to cyclic subgroup, another one is a non-cyclic subgroup. So we found here for the cyclic subgroup of order 4. Now let's move for the non-cyclic subgroup of order 4, okay? If our group which is isomorphic to non-cyclic subgroup of order 4, okay, that means it's isomorphic to Z2 cross Z2, which is a non-cyclic, okay? Why it is non-cyclic? There are two ways we can find that one as a non-cyclic or non-cyclic, okay? If M Zm cross Zn, okay? If M and N has GCD1, then it is only cyclic subgroup, okay? But it is not the GCD1, so we cannot say that the cyclic, okay? And another one is there does not exist. So order of group Z2 cross Z2, which is having order of group is a 4, but there does not exist any element which order is 4, okay? That means order of group and order of their elements are not equal. And when this happen, we say that our group is not cyclic, okay? So this is non-cyclic group of order 4, okay? So element of group of order 4, but there does not exist element whose order 4, okay? Now let's find out the element which contain in Z2 cross Z2, okay? So we know that Z2 is the integer group, okay? So Z2 contains 0 and 1, only 2 elements, and this Z2 contain again 0 and 1, and we have the Cartesian product between that, okay? So go for their elements, okay? So Z2 0 1 and again next Z2 is a 0 1, okay? So take that 0 product with the remaining elements. So 0 1 0 0 1 0 1 1, okay? This is the possible elements which present here in our group Z2 cross Z2, okay? So now next we have to find out the subgroup, okay? So we have to find out whether this Z2 cross Z2 is isomorphic to our subgroup or not, okay? Our subgroup means we have to take that subgroup from our Quaternion group. So Z2 cross Z2 is isomorphic to it, that subgroup or not, okay? So we know that Z2 cross Z2 is having 3 elements, okay? 0 1 1 0 and 1 1, okay? Whose order 2? Why order 2? Because we have to take their LCMs, okay? Order of 0 which is 1, order of 1 is a 2, order of 0 is 1, order of 0 is 1. Under Z2, okay? We have to take under Z2. Again, order of 1 is 2, order of 0 is 1, order of 1 is 2, and order of 1 is 2. How I found this one? Because we have to check a to the power n identity, okay? And 1 to the power, what we take, then we get the identity element. And under Z2, which is an additive group, we have identity element as a 0, okay? Under Z2, remember, multiplicative group always having identity element 1 and additive group having identity element 0. So we have here identity group, which identity element is a 1, okay? So we want the power of that one where we get the 0, okay? So when we get the 0, 1 to the power 2, 1 to the power 2 is possible. It is the 0. 1 to the power 2 means 2 into 1. It is the property in additive group. So 2 into 1 is a 2. And under Z2, 2 is a 0, which is identity element, okay? So we get the 2 here. So LCM, take the LCM for these elements here. LCM of 2 to 2, 2 1 2, 1 1 1 and 1 2 2. So that means these are the order of these elements, okay? Which present in Z2 cross Z2. So we have 3 elements whose order 2 and only 1 element whose order 1, okay? But in our Quaternion group, we have only minus 1 whose order is 2, okay? Minus 1 only the element whose order is 2. Remaining all other element whose remaining all element is having order 4 and 1, not a other element whose order 2, okay? Only minus 1. That means our H is a subgroup of Q4, then Q4 has at least 3 element of order 4, okay? But Q4 is having only 1 element whose order is 4, okay? But Q4 is having exactly 1 element of order 2, okay, which is a minus 1. But here we have 3 element whose order 2, okay? So we can say here our H does not isomorphic to Z2 cross Z2 because it does not have the element which is there in a Q4, okay? So their subgroups are different. So the non-cyclic subgroup not possible here. And last one, H6, okay? The last subgroup is a Q4. Why Q4 is the cyclic subgroup of our group? We know the one result from group theory, which is the identity and group G are always subgroup of group G, okay? Identity and group G are always subgroup of group G. So here we got the H1 as identity and H6 as the group, a cyclic subgroup of our group, okay? So by using this result. So I hope so you all have understood my today's lecture for finding cyclic subgroup of our group, okay? This is most important topic in different type of exam, and also it is most important in at college level also. So I hope so you all have understood my today's lecture. Thank you everyone.